LIGO seminars these days. Let's see. So I'm actually running out of jokes.
But you have Rana there.
Well, I do have Rana. Actually, it turns out September
That's enough,
1980 was a fairly significant time for both Rana and I. I came out to Caltech to start my work in gravitational waves, and Rana started first grade that month. And we both basically know about the same amount. I know almost as much as he does about gravitational wave interferometry by this time. Rana actually got started with LIGO when he was an undergraduate at the University of Florida, working with Dave Reitze and Dave Tanner. He worked on the input optics, and in fact, one of the widely used photos from the early days of LIGO showing that we were actually making some progress towards getting these things operating was Rana with the mode cleaner, a television picture of the mode cleaner locked in at Hanford. Of course, it was locked on the 1-0 mode, which is the wrong way for it to be locked, but nonetheless, he was smiling, and that was a widely used photo. He then went to MIT, where he's got his PhD working with Ray Weiss. He actually didn't spend very much time at MIT because he spent most of his time at Livingston, where he was responsible for actually making the Livingston interferometer the most sensitive interferometer in the world for several years, until he actually got a chance to work on the Hanford interferometer. And then he came here almost 2 years ago as a postdoc. Ron?
Thanks. Okay. Usually when I talk recently about noise, because noise is such a problem for me. But today, there's an empty seat here. Today I'll only talk a little bit about, maybe half about noise, and half about the other part of our game, which is the signals. So I'll talk a little bit about the interferometers we have today, and then go into interferometers we will have soon, tomorrow, or in the next few years, and then what things we can do to really optimize those interferometers and get the most gravity wave information we can. So this is a plot from Google Earth of. Let me get rid of this little thing. There. Let's try again. All right. So from Google Earth, this is a shot of the U.S. and where our interferometers are. Here we are today, and then we have a couple interferometers in eastern Washington state, and then one in southeastern Louisiana. And they're separated by 3,000 kilometers, or 10 milliseconds for the light travel time. And this is where I went to first grade. It's just, I found it on there, so I had to put it there. Here's some more shots of it. You can see right away the difference. The Hanford interferometers are located basically in the desert. There's not a lot of trees, not a lot of people. The Livingston interferometer is located in a pine forest just about an hour north of New Orleans. And to contrast with it, there are people around. There's you enter the site through here. At this end of the site, at this end of the arm, and at the other end, there are people living close to the buildings. So it's a different environment. And then I'll jump right away to what the interferometers are now. I didn't fill in these numbers. I didn't have time to do that. But the green curve that you see here in units of strain per root hertz, the spectral density of strain per root hertz, is the science goal for the 4-kilometer interferometers over this frequency band. And the red curve and the dark green curve, which are pretty much right on top of it, are the noise curves of the best noise curves that we've gotten out of the 4-kilometer machines up to now. And the blue one is the noise of the 2-kilometer machine. And you can see it's better than within a factor of 2. So it's actually doing pretty good considering its size. And a little band over here, It's a close thing, but I would say the 4-kilometer interferometer at Hanford is even better than it was designed to be. And it's pretty amazing to me that it's gotten here. It took several years, but they're doing very good. And so I said, it says best sensitivity here, so to be fair, I should say this is the data taken at around 3 a.m. on a Sunday morning. And during the daytime and in the weekdays, it's a little bit worse. It's maybe 10 or 20% worse. But this is one of the things we're working on. And over the course of this year, we hope to cut that 10 or 20% down to 5% or so. The numbers that were supposed to be over here, which somehow fell off, are the RMS strain in a band of about 100 hertz around the minimum. And another way to state what the science goal was of the interferometers was that the RMS strain noise in a band of 100 hertz around the minimum should have been 10 to the minus 21 strain RMS. And so as you can see, I've forgotten what the exact numbers are, but they're around 4 or 5 times 10 to the minus 22. So by that figure of merit, they're about 2 times better than they were supposed to be. And a couple things that would help us a lot in the future would be to reduce these big spikes. And I'll talk a little bit later about where they come from. So now the LIGO interferometers are joining almost a worldwide array. In the US, there's the 2 interferometers, 2 sites I talked about. In Germany, there's a 600-meter interferometer in Hanover, Germany. There's a French-Italian collaboration that has a 3-kilometer interferometer in Pisa, Italy, and a 300-meter interferometer in Japan. And then a site for an interferometer yet to be completed in Australia that would complete or really add to this network. And the network is more than just an array of instruments. It's starting to really get to be an exchange between people, and there's a medium amount of travel going on of people who are really experts in each of their interferometers going between sites and sharing information. And that's really been great to see what everyone else is doing and sort of problems with their detectors and problems with our detectors getting shared. And also we're beginning the sharing of data to begin a real network analysis between all of the interferometers. So this is a timeline of where we are. We're now on the left-hand side of this, in the middle of the 5th science run. This is expected to last about a year and a half. And then after that, we'd have 4 years until we upgrade the interferometers to the advanced LIGO. I'm not going to talk any more about it, but we have some plans between now and then to make some modest improvements in the sensitivity and maybe a factor of 5 to 10 increase in the event rate. And that's sort of the goal for the 4 years between the end of this science run and the beginning of advanced LIGO. This red statement is really meant to apply to the end of this time, after we have all the interferometers going. We would, for the first time, I think, have between 3 and 6 very high sensitivity interferometers running all over the world. And this is really an unprecedented amount of sensitivity, both in terms of just pure strain and then also the amount of coverage we get over the sky. That's all I have to say pretty much about the initial LIGO interferometers, and I'll go into describe a little bit how advanced LIGO works. The idea is that it'll be about 10 times more sensitive and detect gravity waves down to 10 hertz instead of 40 or 50 hertz where the initial LIGO interferometers work. Right now we're in the phase of designing and prototyping a lot of the hardware that goes into it. And the idea is to begin installation early or in the middle of 2011 and then improve the sensitivity over a couple of years and be taking science data in 2013. And this is a graph probably a lot of you have seen. This is to start comparing the sensitivity of initial LIGO to advanced LIGO. In the center here is a little gray ball, which is supposed to represent the range of the detectors as of early 2003, when the second science run went on. And this line coming down from the purple box is sort of the the range of the detectors now, or what they're supposed to be when we meet our design sensitivity. And then sort of zooming out, now this gray ball is now the sensitivity of the initial interferometers, and the big ball is the number of sources we'd be able to see with the advanced LIGO detector. So I'll now tell you about how the optics work and why the advanced LIGO interferometer is so much better. The basic idea in all of these schemes is that we have a Michelson type interferometer where some laser beam comes in, splits in two, and then comes to this output port. And this output port is nominally dark, or the interference between the two arms is destructive. And when a gravitational wave passes through, there's a little bit of phase shift in these arms, and you get a little bit of light coming out. To add to that somewhat, we put mirrors in the arms to make the light bounce back and forth about 100 times. And these are so-called Fabry-Perot cavities. These are the things that take up the 4-kilometer beam tubes that you see. And they give us this about a factor of 100 in the sensitivity. To amplify that even further, we put yet another mirror here, and this makes the entire system into one gigantic cavity, complex cavity. And for the advanced LIGO interferometers, we expect to get about 125 watts into the system, and so 2 kilowatts here, and about half a megawatt in the arms, which is really an incredible amount of power. Now, all this that I've shown you so far, if you ignore these numbers, this is the basic configuration that we're running with now, what the initial LIGO interferometers are. And the main difference in the optics is that an extra mirror is added at the output port, and this is called a signal recycling mirror. And what this does is the same way this power recycling mirror did. It forms another complicated resonant cavity with all of these mirrors. And the idea here is in the name. It's to recycle the signal, or to enhance the signal, the gravity wave signal, by shooting it back into the arms and making it interact with the gravitational wave for a little bit longer, and to get some more phase shift and more signal out of it. And so how does that really work? Well, this is a little bit of a cartoon. This short cavity here with the purple high power in it is supposed to represent the combination of these two arms, or the differential mode motion of these arms. This extra short cavity on here is the signal recycling cavity. This is what's formed by the signal mirror that's added and the arm cavities. The effect of making this kind of a complex cavity is normally just that you get a lot more storage of the light. But if you do the trick of detuning this signal cavity by a little bit, you get a picture which kind of looks like this cartoon on the right, which is that if the main laser field is here, the resonant cavity has a shape like this, and gravitational wave sidebands, which are spaced a few hundred hertz off, one of them, the upper sideband, would resonate in the full system, and the lower one not. And so you do your signal readout by reading out basically the upper gravitational wave sideband. And to compare with the initial LIGO, so the scale here is arbitrary, and I've just matched them up, but the shape of the interferometer now is like this. There's a roll off around 100 hertz, and most of the sensitivity is around here. In the advanced interferometer, there's a resonance which is at 150 or 200 hertz. It's tunable, but it's placed here, and it gives you this extra signal gain, and you don't really lose anything for it. There's another piece to what differentiates the optical response of the advanced interferometer from the initial LIGO interferometer, and that's this optical spring that everybody has heard about, I think. What this comes about from is that we have a lot of power in the interferometer, half a megawatt in the arms, and it's just from radiation pressure. The force from radiation pressure, it's 2 times the laser power over the speed of light. And normally that wouldn't give you any kind of a spring effect, but because of the signal recycling cavity that we've got, the arm cavities are tuned a little bit off resonance. And so this gives you a change in the amount of power as you change the arm length. And so this gives you a changing force with length, and that looks like a spring. And this was actually seen just recently at the 40-meter prototype across campus. This is a plot of the response of that 40-meter interferometer to an applied force, or to an applied force where the 1 over f squared dependence that you'd get from pushing a free mass has been divided out, just to get it on a nice scale. And all of these different traces on here are show you the change in the optical spring as the laser power which is stored in the interferometer is slightly changed. So altogether, what does this give you? You get half a megawatt in the arms, and this gives you what's called a kind of like an optical bar detector, because it's so very stiff from having so much power. To give you an idea of it, it's for advanced LIGO, it's about 75 hertz. It's very close to what the 40-meter sees. And one of the consequences of having such a stiff resonance, I mean, these are macroscopic mirrors we have in the interferometer, and to have such a high resonance, high frequency resonance, you really need to have high bandwidth servos. And so the whole control system has to work at time scales of 10 milliseconds or so. The optical spring stiffness, said in another way, is 10 to the 7 newtons per meter. And so it's a big number, but to compare it to something real, I measured the spring coefficient of a BMW Z4 here in the parking garage. This is only 10 to the 4 newtons per meter, and this is on a Z4 with the sports package. And I don't really know anything that stiff. So, and this is a pretty stiff suspension, but the interferometers are going to be very, very, very stiff. No longer, we should probably no longer regard them as being free masses. So this is a plot of the sensitivity of the advanced LIGO machine compared to the initial LIGO. The black curve here is the strain sensitivity of advanced LIGO, and the orange one is the strain sensitivity of the initial LIGO. The one thing I want to draw your attention to in the beginning is these two little bumps. And these are the things I was just talking about. This lower bump comes from having this optical spring. The spring resonance is around here. And this higher bump here comes from this signal recycling cavity enhancement. And so the combination gives you this more complicated shape we have. There's two other main differences between the initial and advanced interferometers. I've got these blue ellipses showing you two aspects of this. On the initial interferometers, the mirrors are suspended from a single loop of wire and on top of a stack of masses and springs. And there's this very steep roll-off here where seismic noise comes down. It's f to the 12 or so. But in advanced LIGO, the design is such that there would be a reduction by a factor of 10 to the 9 in the seismic noise beyond that which we already get from initial LIGO. And that's sort of really changes the character of the instrument, I think. It's no longer limited by seismic noise at low frequencies. The other really impressive improvement is the improvement in the suspension thermal noise. Since the optic is suspended by a loop of wire or some kind of fiber, you have to worry about thermal fluctuations and then fiber getting into the optic and moving it around. And the main difference is that in advanced LIGO, the optic will be suspended by fused silica wires or ribbons, which have much less thermal noise. And so there's a factor of 100 reduction here. And so those two things are what really open up this low frequency band for the interferometer. And then at high frequencies, we have what I'll talk about a little bit more is this unified quantum noise. And in the minimum here, I don't have much to say about this, but we're limited by the thermal Brownian noise and the dielectric coatings on the mirrors of the interferometer. So, so the main point of this, and which I'll now get into, is that this quantum noise we have, which is almost limiting us throughout the whole band, it's tunable in frequency, which means the shape can change and the overall level can change. And we have a bunch of knobs in the instrument which we can use to tune this. But we have to somehow choose what what frequency response we want and what kind of noise curve we want. And this has been done already to some degree, but I think we should do this by looking at all of the sources that we want to detect. Oh, so this is, I should say what this is then. This is a in-spiral of a black hole and neutron star, well, the movie of one that I got from the NASA Goddard site. So I'll just let that play for a little bit. It's kind of impressive. So the neutron star has been disrupted, and so there's the gamma ray burst that comes at the end, and it'll keep looping a little. So I want to talk about how we tune the interferometers to detect these different sources that we have. We have, in 4 broad classes, we have periodic sources, which are most generally, usually what we talk about for periodic sources are pulsars, somewhere in the Milky Way or beyond. One of the main sources we talk about is in-spiraling compact objects, the in-spiral waveforms, the merger waveforms, and then the ring down of the final compact object. We also look for broadband bursts, just all the way out to several kilohertz, and these are things for which we don't know the waveform. And then I won't talk about tuning for this, but we're also, many of us here, looking for stochastic background radiation of gravitational waves. One new source which people here worked on is the possible association of neutron star in-spirals or black hole neutron star binaries with the short hard gamma ray bursts that were detected recently by Swift and HEDI 2. One of the reasons this is so exciting for us is that even for the initial LIGO interferometers, it's possible that the rates could be few or several per year, and this is really quite a change from the past, where all of the sources we talked about were of order of 1 per every few years. And so I think it really deserves some attention, both in the initial interferometers and how we tune the final interferometers. And this, so the same credit here goes to the previous movie. It's from the same site. So one source which the baseline LIGO design is optimized for is the neutron star binary in spiral, and that's the movie that was on this page. That source has most of its energy in the low frequencies here, below 100 hertz. And so this plot over here on the left is the baseline advanced LIGO sensitivity curve, and in it assumes 125 watts getting into the interferometer, and a tuning of the signal recycling cavity, which is 5 degrees off from being resonant for the carrier field. And when you do that, you get this kind of a double dip shape, which I've already showed you. On the right here is the integrand of the signal. So if you take the in-spiral over the whole time before merger, and you look at how much signal-to-noise ratio you accrue at each frequency until over the whole band, this is what you get. And so the units here are arbitrary, but to get the full signal-to-noise, you would just add up the whole area underneath here. And you can see most of our stuff here comes from around 50 hertz, and which is actually a little below the dip. And so still, this is the best tuning I could get by adjusting these parameters to optimize for this source. And just to show you how that looks, if you move the laser power around and the detuning of that signal cavity, you get a surface plot that looks like this. And here so the color axis is in megaparsecs, and that goes from 0 to almost 200 megaparsecs. And so not surprisingly, the peak sensitivity is where the laser power is the highest. And this whole area here of integrand increases because this sort of high frequency part of the noise curve goes down as you increase the laser power. And then as you tune, it's covered up now here, but as you tune the signal recycling cavity, this little peak here moves around, and this is brought down here to emphasize the sensitivity where most of our integrand is. But if we go to a different source, to 30 solar mass black hole pair, these numbers aren't special. They're just chosen to emphasize a different frequency band. We get sort of a different tuning here. You can see the noise curve now just looks sort of like a notch. It's a very, very narrow band instrument in this case. And it's kind of a different story here. Now instead of 50 hertz, most of our signal is coming from 30 hertz here. And so if you were working on the sensitivity and you really wanted to go after this source, you'd really aim for here. The other important thing to look at here is, for this tuning, what's happened is that, or the optimization has sort of asked for a very low laser power. So instead of the half a megawatt or so, which I talked about before, we'd have instead, 5,000, maybe a few hundred kilowatts only, or less in the arms, maybe 50 kilowatts, and pretty far off from resonance. And so it's not surprising. We all know that black holes have something with that much mass has a lot of its energy at low frequencies. And the same plot, to compare with the previous tuning for neutron stars, if you again plot the same black hole sensitivity versus these two parameters, you get this kind of shape. And this is the same scale, or the same x and y scale as the previous one. And so in this case, if you had tuned the interferometer for detecting neutron star in spirals, you'd be sort of over here in this kind of orange area. And so you'd lose about a factor of 2 in the sensitivity for black holes with this kind of mass.
So in this tuning, the laser power, we know how to turn that up and down. So how do you do the detuning that's going on the vertical axis?
Oh,
Practice.
yeah. So this detuning is in phase of let's see, it's in units of carrier phase. So it's really a microscopic detuning. I mean, 360 degrees here would be 1 micron.
You're basically moving in error.
Yeah,
Right?
yeah. So but only by a tiny amount. It's very small fraction of 1 wavelength, or 1 micron. And I think it can be done live. I've watched this happen at GEO in Germany, and there it's a little violent when it happens, but they don't have a digital control system, so they actually there's actually a function generator sitting on a shelf whose frequency changes, and they lock to the frequency of that, and it's not a very continuous process, so it goes in these sort of steps, and the detector makes very loud ka-chunk ka-chunk noises as it settles down. But they're able to tune from 1200 hertz down to 300 hertz without there's some activity and action there, but it doesn't break the lock. And I think we can learn how to do it in an even smoother way and quicker. The laser power, it's also, in the initial LIGO interferometers, it's tuned over a factor of 10 or 20 during operations normally, although while we're taking science data, it's pretty steady. But I think you can also tune it live and think about changing modes within about an hour. That's about the thermal time scale for the mirrors to cool down after you've turned the power down. So this is, I wouldn't really recommend changing modes like this every day, but if we get to the point where detection of neutron star in spirals is just sort of an everyday event, then once we get tired of it, we can sort of switch modes. And the nice thing here is, well, you laugh now, but in another 7 years or so, it won't be so strange. And really, I like this fact that you don't need a lot of laser power. So even if you only have several of these or something, you could, all right, not really with several of these, but with very low laser power, you could still run this thing and do pretty interesting science, I think. So moving on to pulsars, we have in the control room at both of the observatories, we have a monitor which tells us every minute how much more time we have to run until we could detect gravity waves from the Crab pulsar if the observed spin down was entirely due to gravitational waves. And that's a really optimistic estimate for the radiation from the crab, but it's one way to look at how well you're doing for detection of that particular pulsar. So this assumes that the crab's gravity waves are at twice its rotation frequency, and that puts the signal at around 59.6 hertz. And for advanced LIGO, although this is much better than initial LIGO, there's not much you can do for optimizing. So this tuning scheme is not going to help a lot because we're already limited by the Brownian noise from the coating. That's sort of the ideal situation, but the sad fact of life is that in the U.S. the 60 hertz power line is really very close to the crab. It's not right on. So really the magnitude of the 60 hertz by itself is not the killer, but it's the stuff that's right around it. I didn't have a good zoom-in plot, but you can sort of see this peak that I've circled here is the 60 hertz peak. And although the noise curves are very nice, the 60 hertz in a 8-second FFT is poking up by a few orders of magnitude above the background noise. It really bothers everybody who works on the interferometers. And for a long time, I think we didn't know where it came from. Sometimes it would go down, and sometimes it would go up. Lately, so my ex-thesis advisor went around with a coil pickup around all the buildings, looking to see where he could see the largest source of 60 hertz. And he did this with a spectrum analyzer, a big car battery, and the coil, and looked at the magnetic field right around 60 hertz. And it looks like, and this is consistent with what's also been seen in Hanford, that it's coming in through magnetic field fluctuations. In the past, we've measured the magnetic field right outside the chambers where the mirrors are, and you can make a calculation for how much force this gives and how much your mirror moves. And it didn't really add up in the past. The initial LIGO mirrors are actuated by these magnet coil pairs. You can see there's 4 of them on the face here, and here's a picture of one of the magnets. It's a little few millimeter long rare earth magnet which is glued to the optic. And so right here, right around 60 hertz, although we're not limited by the peak itself, there's little wings to this peak which limit our noise. And so it's not really limited by these fundamental noise sources I was talking about, like thermal noise and radiation pressure, but just sort of junk right around the 60 hertz peak. I don't have a picture of it, but there's a scheme to beat this for advanced LIGO. Instead of having a single magnet here, which has its own dipole moment, a recent idea is to stick another magnet on here, which is of the opposite polarity, and so you'd have a net 0 dipole moment for the magnet. And to move it, this little coil would be placed over one of the magnets and not the other. And so you push on one magnet and not on the other, but the ambient magnetic field sees both. And so you'd hopefully get some cancellation of the magnetic field noise. And then maybe see something at the crab frequency. So there's a lot of other pulsars besides the crab. I talked about the crab because it's, in this plot that I have, it's the only dot that's above the initial LIGO noise curve. For advanced LIGO, though, if you tune to the low frequency tuning, which I showed for black holes, you get into this regime where there are a lot more dots. What these dots are, they're still the same optimistic estimate, but they come from taking a bunch of data from the Australian Telescope National Facility webpage, where they have all of this data, and plotting the expected gravity wave signal that we would get in a 1-year integration, assuming again that all of the energy which goes into, or all of the energy released from the spin down goes into gravitational waves. There's a lot more here in this sort of tuning. I tried to see if there was some sort of tuning that would let us look right at these millisecond pulsars, but this is sort of the best I could find. Although it's still maybe not a bad tuning if there's a very close millisecond pulsar that we don't see in the radio. So now, finally, this is getting back to the GRB source that I talked about in the beginning. For this one, it's pretty much the same story as what you'd get if you just tune the interferometer for looking for neutron star in spirals. This noise curve looks about the same. The laser power is a little bit less because if you assume that the black hole has 10 solar masses, the energy is at a lower frequency. It's still right around 50 hertz where all of the sensitivity comes from, and really this plot, if you don't look at any of the numbers, looks at the same, pretty much the same as the neutron star plot I showed. The range is a lot more because the energy is a lot more. Just changing these two parameters, you can find the tuning which gives you a range of 400 megaparsecs for this source, which is really, so it's a factor of 2 above what we'd get for just a neutron star pair. It's still a pretty big number, but there's even more that we can do to get more sensitivity for this source. So far I've been talking about just changing the laser power here and this length microscopically. So the length of this cavity and the amount of power entering the interferometer. But there's a couple other knobs we can change, and not live, but ahead of time, before we actually get the mirrors coated and polished, we decide what to do. We can change the Q of the arm cavities by changing the transmission or the amount of power leaking through this mirror. And then we can also change the Q of the signal recycling cavity and try and use that to optimize the range. Now, it's not, I say this, but it's a little hard to do all of these things because when you have just 2 parameters to change, it's not so bad. It's just a 2D plot, and you can see just by looking at the color what you want. But once you get to more than 3 or 4 dimensions, it's not so easy to plot. But you can still, on this guy here, it takes about 2 hours to run all of these cases and see what kind of sensitivity you'd get. And you can do pretty good. You can get a 30% improvement over what we had without changing those knobs. So this is again just one choice of black hole mass, 10 solar mass and 1.4 solar mass. The noise curve looks a little bit narrower, but you now get 530 megaparsecs as your range. And this tuning, you'd be running with 1/5 of the laser power, a lot more detuning of the cavities. And the big difference is the change in the losses a little bit. You make both the arm cavities and the signal recycling cavity very low Q, or it's changing these numbers by about a factor of 2. And so this 530 megaparsecs, I should say, it ignores tidal disruption. And so it just assumes that you go right on in and accrue signal to noise right up to the ISCO, or the innermost stable circular orbit. So that's all the tuning I was going to talk about. Just to summarize, the initial LIGO interferometers are going now, taking data for another year or so. Hopefully we'll have results from those soon, in April or this summer. We have some hardware improvements in mind for just afterwards, for the next few years, which look promising. And then we're gearing up and things are looking good for installing advanced LIGO in 2011. But before this happens, what we really ought to do, I think, is to explore a lot more of these knobs and look at really what kind of interferometer we're trying to build. And not for just the few sources I've already talked about, but for any source that the community thinks that we ought to be detecting, and to really take a look at every choice we've made in mirror size and reflectivity and coding, cavity lengths, and think before we actually construct the thing, what's really the best frequency response and sensitivity we can get, and then afterwards we'll start gravitational wave astronomy. So that's all I've got.
Questions?
say anything about, or any details about enhancements that one might do to pick up the sector factor of 2 sensitivity? Could you just give us a short summary of what you think are the choices of things to do and when this would occur?
Yeah. Let me find something to point at. Yeah. Okay. So this is sort of a picture of the interferometer we have now, and the sensitivity. Let's see. I don't have a. I'll point at a plot. So the sensitivity here at high frequencies, and maybe even down to 100 hertz or so, right now is limited by shot noise, or just detection noise, because we have a limited amount of light in the interferometers. And the reason it's limited is there's two things. We've turned up the knob as far as it goes on the laser, so that's as much as goes in. And then on the detection side, we already, using the low noise electronics we have, it takes 4 photodetectors per interferometer to detect the amount of light that comes out, because there's a lot that comes out. The arms are not matched, and so the dark port is not really dark, it's sort of dark. And the way things are running now, we're sort of at the edge of the dynamic range of the detectors, and we're also running out of laser power. So the two schemes to increase the sensitivity in a broadband way, one is to put another cavity on the output. This is not a suspended mirror, but just a short monolithic cavity to clean up the light and reduce or remove all of the light which comes out, which is not a gravitational wave signal or doesn't contribute to the signal. And then the other strategy is to increase the laser power by a factor of a few, 3 maybe, by using some of the laser technology that is being developed for advanced LIGO. And those two things together, potentially, on paper that would give you a factor of 3. Realistically, you never get that. So there will be some extra problems. And so I figured a factor of 2 or 2.5 is a good estimate for what we could get. Well, that's only in this band, and right away you'd say, well, there's that integrand plot that showed all the sensitivity comes from here, and what does that really do for us? So there, as a sort of secondary or tertiary steps, if we figure out what this noise is here at low frequencies, of course we would reduce that, but so far we don't. But just below here, we believe we would be limited by thermal noise in the suspensions. And it's a somewhat riskier thing to do, but if we find out that we're limited by excess, some sort of nonlinear noise or rubbing or something like that in the way that we clamp the suspension wires, we are working on better ways to clamp the wires. And if we get the full, so if there's no excess noise and there's no surprises, and we are limited by just the thermal noise in the steel wires, we would be about a factor of 2 less already than what we are now. So, really, we're not there. And so you might ask, well, maybe it's not such a good idea to work on the reclamping the wires or changing the wires. And I sort of agree. I think we should just figure out what noise is limiting us now and reduce that. And we would be happy with being limited by the fundamental noise sources which the interferometer was designed for. And that would be basically a factor of 2 or 2.5 improvement. And so behind all of those things I said, there's dozens of minor tasks that go into supporting increasing the laser power or putting in new cavities and that kind of thing. But it's about the right amount of work that would take a few years. And I think it's a good thing.
What's the source of the very prominent feature at about 350 hertz?
That's that is the it is the thermal fluctuations of the wire that holds the optic. So it's the first mode of the wire. Yeah.
You can see the second and third and fourth modes as well.
Yeah, there's a pack of them because there's in a single loop of wire, there's a few modes per wire, and there's 4 test masses, and so they're all bunched up around here, and then there's all of their peaks up to here, and up here these peaks are coming from the internal modes of the mirror itself. It's vibrating at a few kilohertz and several kilohertz, and those are there's nothing to do about those.
Questions? So, Rana, you said that a clever way to reduce the coupling of the ambient magnetic field fluctuations is to just have this cancel the dipoles at the mass.
Yeah.
But until we can get around to doing that, which would be very invasive, what's the chance of reducing the source of those fluctuating magnetic fields at their source?
Yeah.
Yeah.
It's a lot of work, Alan.
Yeah, but you don't have to open the vacuum.
Yeah, you're right. Well, yeah, so one big source of the, I don't have a picture of the chambers here, but the chamber looks like a cylinder with a hat on the top. And the little hat on the top is a separate piece of metal than the rest of it. And so there's a gasket that goes around which connects these two. And there's a little vacuum space in there, an annulus vacuum. And there's a little ion pump that pumps that vacuum. And of course, ion pumps work at a high voltage, and so the AC line comes into a transformer that sits really close to that little hat, and then gets transformed to high voltage and pumps the annulus. But in doing so, the transformer radiates a lot of 60 hertz magnetic field. And if you put a magnetometer there and you estimate what the coupling is, it's within a factor of 2 of explaining the noise we have at 60 hertz and displacement. So it's an ongoing project to figure out how to move that transformer away.
Maybe could you use your own power source that wasn't 60 hertz, but say 55 hertz or something like that? Generate your own AC just locally for that particular unit.
Yeah. There are, there are these things you can buy which are called frequency shifters for power. They're big, massive units, and so that's not a bad idea.
Just a small one. I mean, it's a small thing, for a small amount, just for the local units.
Yeah, I'm a little afraid we'd fix one, and then we'd find that it would only drop by 10%, and so I think we ought to reduce the coupling a lot, and then go around.
It's practical to put mu metal around it. It's probably so huge, isn't it? It takes so much.
It's huge. I think the mu metal would just saturate right away.
And I just comment on your point about the comparison of the stiffness of the optical spring compared to a spring that was cut of a car.
Yeah.
There's well, it's always struck me that one of the things is, of course, the stiffness is very stiff, but especially considering that the ends of the spring are 4 kilometers apart. So a steel thing that length wouldn't be as stiff. But another point, I was just wondering, I think also that there's a comparable stiffness from the feedback control system that feeds back to the test masses. I think that must be comparable. I'm not sure exactly whether it's bigger or less than the optical spring. It's comparable, isn't it?
Yeah.
Yes, that's also a very stiff thing. It's a kind of virtual stiffness.
Yeah. Well, and it's real there, and
That's real.
and it works even up to higher frequencies.
That's
but
right. It depends on how where unity gain frequency is for your servo.
Yeah, and right.
But those things are quite impressive. Those stiffness numbers.
Yeah, and they still work. Yeah.
So what do you know about that excess noise around 40, 50 hertz?
Oh, yeah, not enough. We've made a lot of tests, so I can say the things that it's not. Well, you have to start somewhere. So one thing that people had always told me when in the beginning days when we were installing, I think maybe Stan was showing me how to install suspensions when I first started, and people said, oh, this is never going to work because as the suspension moves and the wire moves around, you'll have rubbing around the clamp, and you'll have all sorts of, there's no way you can have this steep of a wall in reality. I mean, this thing, which is in meters, it's around 10 to the minus 18 here and goes up to 10 to the minus 6 at low frequencies. it really assumes a high degree of linearity in the system, that there's no way motion at a few hertz is going to double and triple and quadruple and show up down here. And so we made a lot of tests, and probably the best test is to simulate real ground motion. And so what you can do is turn off some of the control to the pendulums and just let them pendulate. They just ring up after several minutes at their pendulum frequency, and they build up sort of several microns of motion. So you get it to be 10 times more than the ground motion, and you find that it doesn't increase the noise at all. So that rules out excess motion because of the wire and the clamping and that kind of thing. And you can also think about, well, maybe there's too much angular motion, so we increase the angular motion a lot, and that doesn't do it. And then we thought maybe some of the detection electronics or something like that would have excess noise, so we drove extra signal into those and put a lot more noise on there, and that doesn't increase it. So that ruled out a lot of good ideas. A lot of things we knew how to fix are not the problem. One thing that's left that does produce excess noise is if we just put extra force in and at low frequencies, at 1 hertz or so, not the pendulum frequency, but maybe 50% higher or something like that. And if we drive up the interferometer and give it a few microns of motion at that frequency, we do see that the noise right here will go up by a factor of 2 or so. And so that tells us, I think, that the noise is associated with it's either extra voltage in the electronics that control the optics, or it could, what's worse is it could be associated with just applying extra force to the mirror, in which case, you can imagine scenarios for that. There's the Barkhausen noise, which just comes from flipping in magnetic domains in the magnet, and that as you apply large DC forces, the magnetic moment itself is fluctuating because of all the little domains flipping, and so your large low-frequency motion gets upconverted into AC mirror fluctuations. I hope it's not that, because there's not a lot to do for that. So we've got some tests to go on in the next month or so, where we'll try to put extra noise in through all the various electronics and make sure that they're not to blame. And I'm kind of afraid that what we'll find is that there is no excess noise in any of the electronics, and then I don't know. We can think about replacing the magnets, although I think nobody will agree to do that.
I've often thought maybe to try to avoid using permanent magnets at all, and see use RF inducing currents in copper conductors.
Oh.
Be much cleaner, with no magnetic material at all. I mean, you use an AC field.
Yeah.
You use the induced currents in copper on the conducting.
Well. Yeah. And that, yeah.
It's a little harder to do.
It's harder to do. Yeah. Yeah.
Any questions? Well, let's thank Roger.